Tornadoes and hailstorms are some of the most damaging natural disasters in the world. Thanks to tools like modern weather radar and a new lightning mapper, weather forecasters can give advance notice for people to take cover. But what if there was a way to give even more warning? Help may come from satellites. In 2018, researchers published a paper showing a connection between severe storms and cloud plumes that flow like smoke out of them. They compared hundreds of plume storms with radar, lightning data, and severe weather warnings. Storms that were strong enough to make these features, called above-anvil cirrus plumes, or AACPs, were also more likely to have severe tornadoes, large hail, and high winds. They often appeared 10 to 30 minutes before severe conditions on the ground. Spotting an AACP could save lives by giving people more time to duck and cover. It could especially help in places without radar. Until now, researchers haven't fully understood how the plumes form. But a new study provides some insight into that question. Scientists simulated an AACP using a numerical model and environmental conditions known to produce severe storms. Typically, storms stay in the troposphere, the lowest part of the atmosphere where we live. When these storm clouds rise and reach the stratosphere, they often flatten out, creating an anvil-shaped cloud. In stronger storms, the air rises much faster and higher. The clouds punch their way into the stratosphere and create features called overshooting tops. AACPs are the wispy cirrus clouds that form near the overshooting tops. In the new study, researchers examined how these plumes formed when fast stratospheric winds collided with an overshooting top. The winds flowed up over the top and then plunged downwind so fast they caused something called a hydraulic jump. Hydraulic jumps are easy to see in features such as dams or rivers. When water flows too quickly, the flow will abruptly change. The hydraulic jump is where smooth flow becomes turbulent. They're also common on the backsides of mountains. Fast winds flowing down mountainsides often leap upwards when they hit a barrier to their flow. That's why a plane landing near a mountain might take you on a bumpy ride. Curiously, the new model showed the storms acting like a solid mountain or river rock, even though they're made of fluid. The stratospheric winds had to move around the storm. In the future, the scientists plan to study the role AACPs play in climate change. According to the model, plumes can shoot more than 7 metric tons of water per second into the stratosphere. Since water vapor acts as a powerful greenhouse gas in this layer, the plumes could warm the lower atmosphere even more, creating a cycle of rising temperatures. If the researchers can use tools such as radar and LiDAR to confirm their model, our understanding of severe weather and its climate impacts could take a big leap forward.